In this video, we're going to do our fourth example problem using the equations for constant acceleration motion. So here's the problem. We have a drag racer. The drag racer is going to start from rest and accelerate at 6 meters per second. But 100 meters from the starting point, the drag racer hits a nail. And after that, the drag racer decelerates, coming to rest after covering a total distance of 280 meters. So we want to find the deceleration of the racer after hitting the nail, and then the total elapsed time for the entire process. As with our earlier kinematics problems, we're going to be using the handout. So step 1, draw a clear sketch illustrating the problem. And you can see we have the beginnings of a sketch. The sketch will be developed as we proceed through the process. Step 2, coordinate system. So I put in the x-axis already. Let's put the origin at the position where the drag racer starts. Okay, step 3, identify and number the moments of interest. At this point, I would invite you to pause the video, draw in the moments of interest and number them as well. And then you can even go on to step 4, where you introduce the symbols we're going to need for the different kinematic quantities. Okay, so our first moment of interest is where the drag racer starts. So we will call that moment of interest 0. Let's stick the nail into the picture. So here's the nail. And let's say this is the drag racer hitting the nail. Pop. Let's call this moment 1. And after that, the drag racer decelerates, coming to rest over here. We can call that moment 2. This is where the drag racer stops. We have two options here. Option A, constant velocity problem. Option B, constant acceleration problem. This isn't exactly a constant acceleration problem. We have one constant acceleration from 0 to 1, and a different constant acceleration from 1 to 2. So not quite a constant acceleration throughout, but close enough. Let's go with option B. And with option B, we go to moments 0, 1, and 2 and put in symbols for time, position, velocity. And then we're going to put in symbols for the acceleration beneath. So let's do that. So at moment 0, we have time 0, position 0, velocity 0. At moment 1, we have time 1, position 1, velocity 1. And at moment 2, we have time 2, position 2, velocity 2. Now we have two different accelerations. We have one acceleration going from moment 0 to moment 1. Let's call that A01. And then we have a different constant acceleration going from moment 1 to moment 2. Let's call that one A12. Okay, and if you have not already done so, I would encourage you to pause the video here and see which of these values you're able to fill in. All right, we can say that the process starts at time 0. We already put the origin here, so x0 equals 0. And the problem says that the drag racer starts from rest, so let's put in velocity 0. Now, as far as this moment right here, where the drag racer hits the nail, all we are given is the position, 100 meters, so we can put that in. And then where the drag racer stops, we are not given the time. The position is given here as 280 meters. And we are told that the drag racer has stopped, so let's put in velocity equals 0. As for the accelerations, A01, that's given as 6.0 meters per second squared. And A12, that's what we are trying to find in part A. We do not know that yet. Now let's move on to part 6 of the process, which is to find the equations that we need to solve for the unknown variables. In part A, we're trying to solve for the deceleration of the racer after hitting the nail. In other words, in part A, we're trying to solve for this acceleration A12 that describes the drag racer getting slower after hitting the nail. Now, remember that these equations here only describe a constant acceleration process. We do not have a constant acceleration process all the way through. 0 to 1 is a constant acceleration process. 1 to 2 is a constant acceleration process. 0 to 2 is not a constant acceleration process. In order to solve for A12, we would have to use these equations written so as to connect moment 1 to moment 2. Now, if you go through these equations one by one, thinking about changing the equations so that they connect 1 to 2 instead of 0 to 1, you're going to see that we do not have enough information yet to solve for A12. So we're not ready to solve for A12 yet. Here's what we have to do instead. We have to take the equations as written, connecting moment 0 to moment 1, and fill in this information about moment 1 that we don't have yet. Then we will be ready to solve for A12. Okay, so this would be another opportunity to pause the video, see if you can use these equations to work out time 1 and velocity 1, and then rejoin the video. Now, if you go down the list here, you'll see that in equation 3, the only unknown is T1. But if you would use equation 3 to solve for T1 right off the bat, there would be a quadratic. So maybe we don't want to use the quadratic formula if we don't need to. Now, if you look at equation 4, we know everything in equation 4 except for V1. Never mind that. So we know everything in equation 4 except for V1. So let's just take equation 4 as written and use it to solve for V1. Okay, so we have V1 squared equals V0 squared plus 2a x1 minus x0. Since I'm going from moment 0 to moment 1, then the a here means A01. Okay, now substitute in V0 is 0, x0 is 0, and then taking the square root of both sides, I have V1 is equal to the square root of 2a01 x1. Now putting in the numbers, I have V1 is equal to 2. A01 is 6.0 meters per second squared. X1 is 100 meters. Now, when I put all this into my calculator and take the square root, I get 34.6. Now, as far as the unit, notice that the unit inside the square root is meters squared over seconds squared. If you take the square root of meters squared over seconds squared, you get meters per second. Okay, so we are on our way. I can take this and put it into the figure. Whoops, wrong place. Okay, now that we have that, let's see if we can solve for time without using a quadratic. So we can use equation 2. So let's take equation 2 as written. That will allow us to solve for time 1. Okay, so equation 2 gives us then V1 equals V0 plus, now we're going from moment 0 to moment 1, so this would be A01, and then delta T refers to T1 minus T0. Okay, so we're trying to solve for T1. T0 is 0. T0 is 0. So we have T1 equals V1 over A01. So V1 we found was 34.6 meters per second. A01, 6 meters per second squared. And putting that into my calculator, I get 5.77 seconds, and I will leave the unit checking as an exercise here. Okay, so I'm picking this video back up after a bit of a technical difficulty, and you can see I've rearranged things a bit. I've moved this calculation of T1 up to the top of the page here, and I have filled in our calculations of V1 and T1. At any rate, at this point in the problem, we have now filled in everything we need to know about moment 1, where the drag racer hits the tire, and now we are ready to proceed with the calculation of A12, which is the deceleration of the drag racer after it has hit the nail as it is coming to rest over here. I would encourage you to try this on your own. So think about this list of equations written so that they connect 1 to 2 instead of connecting 0 to 1. So go through the list of equations, thinking about them connecting 1 to 2, and see if there is any equation in there where everything is known except the acceleration going from 1 to 2. If you can find that equation, write that equation down, solve symbolically for the acceleration, substitute numerical values with units at the end of the problem, and see what you get. So I'm going to solve for the acceleration from 1 to 2 using equation 4. So I'm going to take equation 4 and I'm going to take equation 4 and just copy it up here with the subscripts changed so that I am connecting 1 to 2. So then I have V2 squared equals V1 squared plus 2. Now it's A12, x2 minus x1. All right, you can see that everything is known except for A12. V2 is 0. Nothing else is 0, so we just have to do our algebra. Let me take the V1 squared and move it to the left where it picks up a minus sign. So I have minus V1 squared equals 2A12 times x2 minus x1. Now I'll divide both sides by 2 times the difference of the x's. So this side gets divided by 2 times x2 minus x1. This side gets divided by 2 times x2 minus x1. And you can see that after cancellation, the only thing remaining on the right is A12. So I'm going to flip the equation around, switch sides, and then I have A12 equals minus V1 squared divided by 2 x2 minus x1. Substituting on the right, I have minus in V1, 34.6 meters per second, quantity squared, divided by 2. Now x2 minus x1, that would be 280 meters minus 100 meters. Now, if you put this in your calculator, the numerical value you will get would be minus 3.325. And you could round that off to minus 3.32 if you like. I'm going to leave the 5 there. Now, as far as the unit, let's look at the units here. So in the numerator, we have meters squared over seconds squared. In the denominator, meters. So meters squared over meters gives us just meters. And we get as our unit meters per second squared, as we would expect for an acceleration. So that is part A. Let me go into the figure and put that in. So I have A12 equals minus 3.325 meters per second squared. Okay, let's move on to part B. Part B asks us to find the total elapsed time. In other words, in part B, we are looking for time 2. Okay, now, remember that in this problem, the equations here can be used to connect moment 0 to moment 1, or they can be used to connect moment 1 to moment 2. So think about these equations here, written so that they connect moment 1 to moment 2. Scan the equations and see if you can find one where T2 would be the only unknown. Okay. So I did this using equation 2, with equation 2 written so as to connect moment 1 to moment 2. So for part B, I'm just going to take this and copy it in there. I have V2 equals V1 plus A. And if I'm connecting moment 1 to moment 2, then that delta T would be T2 minus T1. And the A would be A12. The only thing here which is 0 is V2, so let's zero that out. Okay, let's solve for T2 then. So we can start by taking that V1 and moving it to the left where it picks up a minus sign. And then divide through by the A12, so the A12 comes down here. Now I have minus V1 over A12 equals T2 minus T1. So I'm going to take the T1 to the left side where it picks up a plus sign. And then after doing that, flip the sides. So I get T2 equals T1 minus V1 over A12. And substituting T1, 5.77 seconds minus, and then V1, 34.6 meters per second. And then we have A12. A12 we found in the previous part, minus 3.325 meters per second squared. So when I put this into my calculator, I get 16.2, but let's check the units. So the first term has units of seconds. And as for the second term, we have meters per second divided by meters per second squared. Meters cancels meters. Now take that second squared, pop it into the top. You then have second squared over seconds. Second squared over seconds is seconds. So we see that both terms have units of seconds, which is what we want. The unit of the answer is seconds. So the entire process takes 16.2 seconds. And now we have completed our fourth example problem on objects moving with constant acceleration, or in this case, piecewise constant acceleration. And once you have solved symbolically,